I'm going to represent you high-level representations through unconstrained sensorimotor learning. First, I want to start with the question what a symbol is. Symbol can be defined as internal representations of outer effects like environment or other actors. As Neville and Simon phrased in their work, symbols lie at the root of intelligent action, which is of course the primary topic of artificial intelligence. In the literature, there are some work started by assuming the existing of such symbols. These works are trying to utilize these symbols for better learning experience and better results. On the other hand, there are some other works which is trying to facilitate the emergence of such symbols. This approach's main purpose is forcing neural network to create sub-goals for more complex tasks. First, start with the assuming the existence of symbol approach. As you can see from the picture, we just gathered from the Bacon's work, an option is a sub-goal which improves itself to achieve more complex goal. This option could be a symbol. Also, you can see the difference between actor critic and option critic. In actor critic architecture, there is only one policy to follow. On the other hand, in option critic architecture, policy allows the agent to choose the options. After agent chooses an option, it follows its intra-option policy until the option terminates. When the agent chooses another option and follows its intra-option policy until termination. On the other hand, you can see the stalls works in the slide. This approach is forcing neural network to create multiple sub-goals in order to achieve a complex goal. This brings us the purpose of the paper. There are always design biases or choices that promotes the formation of high-level representations. In this paper, by contrast, we investigate the formation of symbol-like representations with no assumptions on the existence of such representations and with no explicit design choice to promote abstraction. To realize non-biased scenario, a reinforcement learning framework is adopted for sensorimotor learning of squat to stand task where a robot needs to learn to generate the joint torques to change its posture from squat to stand without falling over. The task is adopted from our ongoing work on human adaptation to postural perturbations. The robot is composed of an upper leg, lower leg, and a torso. You can see the picture in the slide which shows how a robot looks like when trying to stand. The robot state is given by the joint angles and the angular velocities. Action space is defined by the torques which apply to each joint. To make the task more challenging, the squat to stand task includes a non-trivial perturbation which pushes the robot in the posterior direction with a force. The reward function is given with the height. The episode is terminated when the allowed time of 2 seconds has elapsed or the robot falls. Height of the robot is less than 0.5 meters means robot is falling. Or the robot hits the joint limits, which means greater than pi for each joint. Policy gradient reinforcement learning finds a local optimal policy by following the gradient of the expected total reward of over the episodes. In this study, we used actor critic method that has stochastic policy which is used to sample the actions from the policy exploration and exploitation. Both actor critic network parameter update formulas given in the presentation. A policy network with a single hidden layer composed of 32 neurons has empirically found to be enough to learn the task. The input and the output layers are automatically determined by the state and action spaces. Consequently, the policy network has 6 inputs and 3 outputs corresponding to dimension of state and action spaces. The critic network is implemented as two hidden layer network. The number of neurons in the layers are set as 16 and 32, conforming to small network to ease the analysis. The mean total reward of the 20 times repeated learning can be seen from the graph in the presentation. The shades around the mean indicates the standard deviation. Results A. The emergence of neural encoding of the physical robot state. For the control of the task of squat to stand movement under the perturbation, a key physical meaningful parameter is the position and the velocity of the center of mass of the robot, COM. In this analysis, we aim to detect neurons that may capture COM dynamics, in particular the vertical distance of COM from the ground and the vertical velocity of the COM. For each neuron in the policy network, the linear correlation between neuron outputs and the COM height velocity was computed. Subsequently, correlations of the neuron outputs with COM height velocity were obtained. This allows the visualization of COM dynamics to be represented within the neuron population as histograms. The analysis was conducted after 20K training episodes where the learning was stabilized and the robot was observed to complete squat to stand task movement successfully. For detecting neural representations of the COM dynamics, single trials were performed with the exploration turned off. Learning and testing was repeated 20 times to assess the variability in COM height and velocity representations formed. We focused on the vertical y-axis COM dynamics in assessing the potential physical robot state representation by the neural activity after learning. The correlation analysis of the neural responses during the squat to stand task execution revealed that 6 out of 32 neurons strongly encode the COM vertical position, indicated by the high mean correlation coefficient. Notably, 15 out of 32 neurons also strongly correlated with the vertical composition. The small standard error on the histogram bars indicate the consistency of the robot COM vertical position encoding. The number of neurons that strongly encode COM velocity was less with the lower correlation level compared to the position encoding. On average, only 8 out of 32 neurons had strong correlation with the COM vertical velocity. On the other hand, large portion of the neurons, 21 out of 32 neurons, showed a mid-level correlation, which was not the case for position encoding. Results B. The specialization of neuron populations that are formed via learning. This analysis focused on detecting functional specialization of neurons during the learning process. For this analysis, learning was conducted for 20K episodes until the robot learned to complete squat to stand task. While training was taking place, in every 1000 episode, the exploration was temporarily turned off and the policy network was put in the control of the robot with the current network weights. The analysis conducted in this part not only considers the full squat to stand movement period, but also focuses on 3 predefined phases, being early, the first 0.5 seconds, mid, the middle 1 second, and the last zero point 0.5 seconds of movement segments that roughly corresponds standing up, turning balance, and balanced post stages. To assess the number of distinct neural response patterns in the policy network, the number of clusters are estimated by using X-means algorithms applied to the activity vectors. When the neuron responses are considered for whole duration of squat to stand-up movement while learning, the number of clusters started around 10 and converged to 3 as found by the X-means algorithms. The same X-means clustering also was repeated when the neuron outputs were constrained to different phases of movement, early, mid, and final. The early phase usually corresponds to standing up, whereas the mid phase corresponds to balance posture for the successful trials. The final phase usually corresponds to the time when the robot starts to lose balance or fall. In these specific phases, the converged number of clusters was consistently found to be 5 on average. Therefore, we used 5 clusters for the further analysis using k-means as presented next. Although X-means gives us the number of neural response patterns formed, to see the individual patterns it's necessary to investigate the response profiles of the clusters found. To be specific, the clustering was applied after 2K, 7K, 12K, and 20K learning episodes had taken place. The resulting mean neural response patterns are given in the figure. As you can see, the neural clusters are not very different at the beginning. Specialization starts to appear after 10K episodes of learning. And finally, major robot controller with the distinct responses are obtained when the task is successfully learned. Additional clustering analysis was performed that revealed the organizational relationship among the clusters as a function of the simulation time. During the standing up phase, the first 0.5 seconds, each neuron population had a specific response profile to actuate the robot without a fall. In the mid phase, the neuron populations act as a distinct nonlinear feedback controller to bring the robot to standing posture, and finally the last phase of the neuron populations produced almost constant neural output to counteract gravity. From the general perspective, the constant neural output can be represented as concept of stability, whereas the alternating output pattern of the mid phase may represent the concept of keeping balance. Result C. Response to environmental change. Like early analysis, system was trained for 20K episodes to learn the squat to stand task, slightly changed by reducing the perturbation coefficient from 300 to 290. It was found that neurons show similar patterns in the early and mid phases to the ones obtained with the original setting, probably due to the fact that the perturbation constant change was small. Therefore, further analysis conducted on final phase of the movement, where the environmental change has a dramatical effect of fall versus no fall, in spite of the small change in the perturbation. These neuron activities, especially cluster 4, can be predictive of upcoming fall. Therefore, these neural responses can be used as symbolic representation indicating a pending fall. Conclusion. The analysis of neural responses of policy network revealed that parsimonious physical representations of body dynamics is represented in the neural responses. Certain neural populations in the policy network that learned to implement a stand-up controller form a functional unit that can be used to represent symbol-like constructs during learning. A change in the environment that was not seen before or during the learning that might yield a discrete representations of robot self. Our study supports the idea that basic sensorimotor learning that allowed earlier biological system to survive might also facilitate the formation of symbol-like or high-level representations that were amendable to evolutionary exploitation by high-level additional circuitry. Thanks for listening.